Yeah, hello and welcome everybody to this week's episode of Wissenschaft fürs Wohnzimmer, or sitting room science, since this episode will be in English today. And we're very happy to have Dr. Fernández Méndez as our speaker today to hear her talk about from climate change impacts to solutions, a tale of floating algae from the poles to the tropics. So we are very happy to have you here and hear your talk, since Mar is a marine researcher, but also calls herself a climate optimist, which I find very cool and fascinating. So looking forward to your talk. But if you have, as always, comments or questions, please write them in the chat, and we will forward them to Mar during the talk or at the end of her talk when we have a discussion round. And that's us, the support team of this evening. So before we start with the presentation, we shortly introduce ourselves. So hi, I'm Franzi. I'm a PhD student at the Alfred Wegener Institute. I'm studying the effects of climate change on phytoplankton, so the little macroalgae, in the Southern Ocean, which is around the Antarctic continent. And yes, I will hand over to Matthias.
Yes, good evening also from my side. So I decided, because of the weather, to do like a balcony science tonight. So that's actually pretty nice to sit outside here. I'm also really looking forward to Mar's talk. I actually met her, I think, the first time at a polar science conference in California, ironically. Because I'm also normally not sitting outside or in the colder areas, working in the Arctic mostly with bacteria and climate change and how bacteria respond to the changing conditions in the Arctic. And now I'm also wishing you a very great talk and enjoy the evening.
Hello, everyone. And if we were talking about the weather, and envy a little bit the nice weather that Matthias has. I am in Argentina, so I'm caminera. I am a biologist, and in the moment it is a bit of winter time here. I am working in marine ecology, particularly in the distribution of benthic animals in Antarctica, and I really will like to know more about macroalgae, which are, in my case, one of the most important flora that I'm working. So Mar, welcome, and go for it.
Thank you very much, guys, for inviting me to do this. I welcome you all to my living room here in the ocean. And I will start sharing my screen so that you can see my slides. There we go. Okay, I hope it's working now. Okay, today I want to talk a little bit about the story of my life. So basically how I went from looking at climate change from the side of a problem and the impacts that it causes into ecosystems, and then moving towards how we can find solutions for it. So as you all probably know by now, because it's been in the news and everywhere, the Arctic is melting. And the Arctic is an ocean that is surrounded by land, and it's seasonally covered by sea ice, so floating ice on top of the water. And this ice cover has been decreasing dramatically in the last years. And this is just a symptom that our planet is basically warming. So the water is warming, the air is warming, and basically the Arctic is this very thin layer of ice that is showing us how fast this is happening and how dramatic these changes are. So the Arctic is kind of the canary in the coal mine. And we've known this already for many years. I mean, you see the declining trend. We've seen this in the last decades getting even worse. The Arctic reaching a new stage, so to say. And the problem with the Arctic is that we still know very little about it. And so I was lucky enough, to go to the Arctic in 2011 and in 2012 on Polarstern. And back then it was very exciting to go there because there was still so little known about the central Arctic. So I'm talking really close to the North Pole. And every measurement we did was almost a unique measurement that hadn't been done for the last 20 years. So when I wrote my PhD, I had very little data to compare my measurements to. And it was very exciting to feel myself as an explorer and to try and figure out, okay, how is climate change impacting this very fragile ecosystem? And so one of the things that caught my attention was an algae. So I used to work on phytoplankton, so the small little algae like Francie. And one of the algae that had caught my attention from the literature that I had been reading before was called Melosira arctica. So I saw some black and white pictures of this algae from the Russians. Wait, I didn't want to go that far yet. Aaron? And the Russians were diving in forests, basically, of these really long filaments of this algae. And when I went on Polarst and I asked people about it, and they told me, oh no, this algae is extinct. It doesn't happen anymore in the Arctic because we've been losing so much sea ice. So I was really happy when we actually found it in some of the stations that we sampled. It was not 3 meters long, as I had seen in the pictures of the Russians, but it was 30 centimeters long and it was there. So I was very happy about that. And I got the chance to do some experiments with it and see, okay, what happens when the ice melts? Does it sink automatically to the bottom of the ocean, or does it stay floating for a while? So that was also very exciting. And one question that came into our heads when we saw this is, we have so little productivity happening below the ice, so little biomass, so little algae growing there. How does this Melosira manage to grow so long and so much in such a short time? Because in the Arctic, you only have sunlight 6 months per year. And one of the key questions was, where is it getting its nutrients from, right? And then we developed some hypotheses, and that's what I want to show you here. So here we have the months, so from October, so this is April and this is September. And so in October, when the sea ice forms close to the shelves, so for example, imagine the coast of Siberia, right? The ice forms there, and then this Melosira has spores that can stay in the sediment. And when the water mixes here, it comes to the newly formed ice and it gets entrapped there. And then this ice starts drifting through the Arctic Ocean, following the transpolar drift, like Mosaic did this last year. And as it goes with the ice, it starts taking up nutrients. Even if it's night, even if it's dark, it can suck up all the nutrients in the water and continue drifting with the ice. And by the time it's April, May, when the sun comes out in the Arctic, then it can start producing biomass and it continues taking up nutrients. And the good thing of this algae is that because it's attached to the ice, it basically goes floating over different water masses and it can capture nutrients from different water masses, which phytoplankton can't do because they're kind of stuck to one parcel of water. So this is the main advantage of this algae, and keep that in mind because I will come back to that later. Now, the other thing that we envisioned is that at some point this algae would sink rapidly to the benthos, and actually we were jumping on our seats when we actually found it in the deep sea, 4,000 meters deep in the middle of the Arctic Ocean. You can see it here in one of the MOOC cores that we retrieved. And we also took some images, and you can see here some deep sea cucumbers feeding on it. And what was also very interesting is that this algae sinks so fast that it doesn't really die, it just sinks. And when we retrieve this algae that you see here in this sediment core, and we put it under the microscope, it was actually still living. It was super happy, even though it had traveled 4,000 meters down to the deep sea. So yeah, this was a new discovery. We discovered that this algae is actually hugely contributing to the carbon export in the Arctic. So that was also very exciting. Now, a couple of years later, when I started my postdoc in Norway, I was lucky enough to join the Norwegian Young Sea Ice Cruise. That was a similar cruise to Mosaic, but a little bit smaller. We were only 6 months in the ice instead of a whole year. And the interesting thing, so we discovered a lot of new features of the Arctic Ocean. Because again, we're trying to understand the system that is at the same time changing. So it's like trying to understand a car while it's accelerating towards another status. And so we had discovered in recent years, or the Arctic scientific community had discovered in recent years, that phytoplankton blooms can actually occur below the ice. And what had been reported until then was that they were usually dominated by diatoms. So that's the regular suspects also in all other oceans. However, that year in 2015, the under ice bloom that we observed was dominated by Phaeocystis instead of diatoms. And so these two types of algae have completely different traits. And Phaeocystis, for example, doesn't contribute that much neither to the food chain nor to sinking. So of course, the consequences for the Arctic ecosystem are huge. And another new discovery that we did was that because the ice is getting thinner, but the precipitation in terms of snow is getting thicker, the sea ice in summer was sinking and it was being flooded by the seawater. And so you can see it in this picture. There were actually ponds of like brackish, brownish water below the snow. So this is when we shoveled it away, we could see these brown, green spots. And we call them the snow ice interface communities. And this is basically algae that are coming from the water. So they're not sea ice algae, not the typical suspects from the sea ice, but rather pelagic species that are coming into the ice and start growing in this area between the snow and the ice. And so they're protected from grazers there, and they create completely new communities that we hadn't really observed that often until then. So I was observing with my own eyes, and just by going to the Arctic 4 or 5 times, already changes in the ecosystem at a huge scale. And so, okay, I was like, okay, the Arctic is changing really quickly. What's happening in the other oceans? And then start looking into the literature. And one of the things that struck me the most is that our oceans are becoming less productive. And this is mainly because stratification is changing. So stratification means how the water column is mixed. And so if you have more light and more temperature coming into the upper surface of the ocean, then that gets stratified, it gets stable, and it doesn't mix that deeply as it used to be. Now, what's the problem with that? That nutrients are actually in the deeper layers, because at the surface, they're used up by algae. So if you don't have that deep mixing, you don't have nutrients coming to the surface, or you have less nutrients coming to the surface, and therefore we have less productivity. So I was like, okay, so the Arctic and all other oceans are changing. I mean, I'm sure you've also heard about ocean acidification, plastic pollution. So I was like, okay, there's all these issues with the ocean, and it seems like we're continuing our business as usual. What are we going to do about it? And then when I started looking into, okay, is anyone looking into solutions? And of course, there's a lot of people looking into solutions, but people were basically focusing on mitigation, right? So moving to renewable energies and all those things, which I find great. And we should be doing this, definitely, because that's what's going to turn the curve down towards here. But then there's this blue area. And this blue area, if we want to achieve the 1.5 degree path, which is what the Paris Agreement tries to make people agree to, we still need to sequester some of that CO2 from the atmosphere, because there are some things that are going to continue emitting CO2, even if we change all the others. Even more, and this is not depicted here, if we want to remove all the accumulated carbon emissions that we have put in the atmosphere since the beginning of the Industrial Revolution, we have to develop negative emission technologies to sequester that CO2 out of the atmosphere. That's the reason why Elon Musk and all these very rich guys are putting out money like the X Prize to say, hey, who can give me the best option to get CO2 out of the atmosphere? Because CO2 in the atmosphere is what's causing climate change. Now, of course, I turned towards the ocean. That's what I've always done. And I love my algae and I know that they can sequester carbon. So I was like, okay, the answer must be there. Now, there's a whole range of solutions that have been proposed for the ocean. And I love this figure from the project Ocean Nets that is actually currently trying to model all these approaches to see which one seems most promising. And you can see, for example, here, artificial upwelling, which would actually also counteract this stratification issue, because artificial upwelling means bringing nutrients from deeper waters to the surface to enhance productivity at the surface. Then you also have the blue carbon that you've all probably heard about, so mangroves, seagrasses, and also macroalgae farms. So this is coming now into the picture. And then we have iron or nutrient fertilization. We have alkalinization, which is trying to shift the buffer of the ocean towards alkalinity so that the ocean is able to sequester more carbon. We have also terrestrial biomass dumping. We have artificial downwelling. We have marine biomass for biochar. So there's a whole range of options. And now today I want to talk a bit to start with about artificial upwelling, because that's what I've been working partially during my last postdoc in Ulf Riebesel's group at GEOMAR. And one of the key things that we've figured out is that, yes, you can bring water to the surface and you can create biomass, a bloom of phytoplankton, but it's really important to know in which ratios you're bringing the nutrients up So how much nitrate versus silicate versus phosphate are you bringing up? And what does the biomass that is growing at the surface doing with it? At which ratio, again, is it sequestering that carbon? Because if you sequester it in the same ratio as the inorganic carbon that you bring up, then you're doing nothing for the system. It's a zero balance. Only if you manage to sequester more carbon per unit of nutrient, then you're actually sequestering carbon. So that's a key thing that needs to be taken in mind when talking about artificial upwelling. And for example, all the latest modeling papers about artificial upwelling are not taking this into account. So there's much to be improved in that area. And the other thing is sinking. So phytoplankton, when it sinks, it actually, most of it gets remineralized, it gets used by consumers, by decomposers, and it sinks very slowly. It's what we call marine snow. It basically trickles down. And so what reaches in the end, the deep sea and the sediment, so what is sequestered for the long term, is actually a very small proportion of the amount of biomass that you create at the surface. However, if we look at macroalgae, and we have this wonderful macroalgae that grows floating, just as phytoplankton, it's called Sargassum. This one sinks really fast. It has very few consumers at the surface, and so it's a perfect candidate for carbon sequestration in the ocean. And even better, the ratio of carbon to nutrients that it can do is 1 order of magnitude higher than phytoplankton. So you can basically sequester way more carbon per unit of nutrient that you provide. So it seems like a super exciting opportunity. And so this is how this wonderful floating sargassum looks like. So it can create huge mats in the surface of the ocean. Of course, when it's stretched through greater areas and there's wind, it looks more like this. And then if a storm comes or whatever, it can sink in the ocean, and then the bladders that maintain its buoyancy would be squeezed and it would sink. And this, again, doesn't it remind you to our Melosira from the Arctic? So it has, again, the same property. It floats around, so it takes up nutrients from everywhere. And again, this is all a natural process. We're not inventing anything new. Nature has already all the solutions. Now, what has been happening with sargassum is that because of the amounts of nutrients that have been coming into the oceans from rivers like the Amazon or the Mississippi and the Congo River, it has been exploding. It has been blooming like crazy since 2011. So sargassum used to grow usually in the Sargasso Sea, that is here. But because of a change in the North Atlantic oscillation due to climate change, it escaped the Sargasso Sea, and now it's creating what we call the Great Atlantic Sargassum Belt. And this is like 20 million tons of sargassum floating over the ocean. So that's a lot of sargassum that is, of course, causing a lot of problems when it reaches the coast. And you can see that here, for example. So these are the coasts of the Caribbean that are, of course, hugely impacted by sargassum. And this is a whole issue. Like, you have entire industries trying to figure out how to solve this, because, of course, tourists don't want to go to beaches that are smelly. But that's kind of the social and economical impact. But in terms of ecosystems, these sargassum rafts, when they reach the coast, they basically wipe out the corals, the seagrasses, the mangroves, everything they find on their way. So if we prevent that sargassum from reaching the coast, we're not only protecting also those ecosystems that are actively sequestering carbon, like mangroves and seagrasses, but also we prevent it from decomposing on the beach, because when it decomposes on the beach, the CO2 that it captured goes back to the atmosphere. So if we manage to prevent this sargassum from reaching the coast and we actively enhance its sinking, then we're actually sequestering carbon actively in the ocean. Now, sargassum is way more exciting than just that, because you can use it for a ton of things. So of course you can imagine that there's a lot of people already in the Caribbean and elsewhere trying to figure out what to do with this basically raw material that is arriving to their coast. So I joined like a year ago a podcast that is called the Sargassum Podcast, and we interviewed a lot of entrepreneurs and basically local people working on what to do with this sargassum. And there's everything out there, from bioplastics, biofuels, biofertilizers, even concrete, even feed for cattle and sheep. And that reduces the amount of methane that they put out. So all these uses of sargassum are indirect carbon capture, because you're avoiding the CO2 emissions from creating all these products using fossil fuels. So that's another add-on that other technologies might not have, but that seaweed has, in this case, sargassum. And then the other option is, again, to go, and this is more a vision rather than a reality, that's why it's just painted there by hand, but if you combine artificial upwelling with sargassum in the middle of the subtropical gyres, and you create farms where you have the sargassum sustained and managed, like contained and managed, and it doesn't escape to any beaches. And basically, as it grows, you harvest it and you sink it in bales that do not decompose. This could be a game changer because the amounts of carbon that we need to sequester are huge. So we need to go into the gigaton. So all these processes talking about, a little bit here, a little bit there, they're great and they will sum up for sure. But we need methods that we can upscale and that can be like huge amounts of carbon. And of course, we need to study what would happen to the deep sea. But again, the deep sea is vast, and Matthias will talk about this for sure afterwards. There's huge areas in the deep sea where you could do this and not harm any like huge biodiversity life there. So yeah, this is just ideas, and I'm sure we can talk about that during the discussion. And I want to thank you all for your attention, and I hope I didn't exceed my time a lot.
No worries. It was wonderful. Thanks a lot for the presentation, and with all these great pictures and videos. I think it was super interesting and easy to follow. Thanks a lot. So and before I think we start with the discussion that we will have plenty to talk about, I will just shortly introduce the talk for next week, let me just find that slide. So because next week we will also have a talk, of course. It's going to be in German this time again, and it's from Dr. Ulrike Lehr. She's the head of the policy department at the International Renewable Energy Agency in Abu Dhabi, and she will talk about the things that also needs to be done to get the curve down, which Mar already mentioned, so renewable energies. And her talk is, the title of her talk is Jenseits der Megawatt, was bedeutet der Umbau der Energieversorgung unter Einhaltung des 1,5 Grad Ziels für Wirtschaft und Soziales. So it's going to be about the impacts of how, if we change to renewable energies, how that impacts the economics and jobs globally. So looking forward to this topic. But now I think we're going to start with the discussion. Are there any questions in the chat so far?
Well, there is a comment from Hannah, which I actually also know. She was in our group, or she is in our group right now. So hello, Hannah. She just said that she really enjoyed the talk, and she's a huge macroalgae fan in support of algae farming, and that's basically applauding you to go further ahead in that direction, to think about algae farming and finding actually solutions.
Good to know that there are people that are supporting this, because we will need a lot of hands to make this happen.
Yeah, there's another question in the chat.
Ma, thank you very much for your passionate talk. Yes, thank you once again then for your passionate talk. It's really you share with us your emotion and your the fantastic sargassum that it is. We have one question here regarding sargassum. How do we know that huge amounts of sargassum that sinks to the seafloor will not alter the biosphere down there, say it's Oahu?
Okay, so first of all, that sargassum sinks to the bottom of the ocean is a natural process. So the communities in the bottom of the Atlantic Ocean are used to receiving sargassum. So it wouldn't be a complete stranger. Now, the idea is, if we want to sequester a lot of carbon, we need to sink them in a form that they're not actually integrated in the food chain down there. They're basically bales that are not accessible so that they don't get remineralized. How to do that in the best way, we still need to investigate. And of course, we need to do an ecological impact assessment and choose very well where we're going to do this. It wouldn't be just anywhere. I mean, you wouldn't go to the top of a hydrothermal vent and dump it there. But we need to think about the deep sea is vast, it's huge, and there are really areas where there's only, I'm going to say, only bacteria. And so if you dump them there, the impact is minimal. And I think another thing to keep in mind and to keep things in context is that if we don't do anything, if we don't sequester those gigatons of carbon with whatever method it is, then the deep sea is anyways going to completely change, because the circulation of the oceans is going to change, and then the deep sea will become anoxic because you will not get more water from the surface sinking down in the Antarctic. And so we always need to put things in perspective. Of course, there might be, some bacteria that are changing because they receive more sargassum, or, we don't know, we have to study that. But we need to put those changes in a balance with the changes that are already happening in the biosphere because of climate change.
Yes, thanks again for this clarification. And also, you already mentioned that the having the amounts in mind, it's the thing that I think that's sometimes tricky. But if you compare with all the stuff that we already digged out in coal and oil and so on, so it's kind of equals what has to go back somewhere. So I think that's something that can be easily seen from the inner eye, that it's not helping if we just do small scale stuff.
Yeah, it's like reversing what we've been doing in the last 100 years, just extracting and put it in the atmosphere. Now we need to turn it down. And actually, fossil fuels are nothing more than old algae and old plants that's sedimented in the bottom. So it's just reverting the process, basically.
Yeah, and based on this, there was another question about how we can monitor the effects in the deep sea, because it's kind of deep down, so it's assumed that it's going to be tricky, at least.
Yeah, I mean, that's definitely an issue, and you definitely need an array of researchers and monitoring stations that you can basically access and monitor. And the good news for us scientists is that we will always have a job. And I mean, if you're a deep sea ecologist or deep sea biologist, you will always have a job. So that's the good news.
Yeah, sorry, I have to disagree a little bit. If you say only bacteria, I'm just, of course, defending my little friends, of course, very fiercely. But I mean, of course, things take very long down there, so it's probably not going to make like a big difference. It's probably like a balancing the pros and cons as usual. Now for another question that Hannah again asked, coming back to the beach thing and the pollution, so to say, of the beaches, what would be your solution there? I mean, you already mentioned a few things that can be done with these things, with this floating algae.
Yeah, so the issues in the Caribbean are actually pretty complex, because one of the reasons why sargassum is growing in such masses is because of the extra nutrients that are coming from the rivers. And so if you actually want to completely solve the sargassum issue, you need to tackle the nutrient issue. And so one thing that I've been thinking about recently is, why not actually use the sargassum to basically put it as a filter on the rivers to absorb all those extra nutrients before they reach the ocean. And then that sargassum you collected and you dump it somewhere far away where you're not disturbing anything. Another option could be to create concrete from sargassum and then create artificial reefs to restore all those damaged ecosystems in the Caribbean. But definitely the biggest challenge is to actually capture all that sargassum before it reaches the coast, because sargassum is floating and it moves with the wind and so on, and it sometimes disintegrates in little patches and then it aggregates again. So it's not that easy to track and monitor. I mean, we have satellites, but I think drones would be better in that sense, for example, because they have a better resolution and a better scale. But you need a lot of boats, a lot of barriers to prevent that sargassum from reaching the coast. Yeah.
Thank you. We had also another question from the chat from Ole Müller that says, if you look down there, do you find old lumps of sargassum?
Yeah, a lot. Like so close to the coast of the Caribbean, there's a lot, because part of the sargassum that reaches there, instead of landing on the beach, it ends on the bottom. And in the middle of the Atlantic, you also find quite a bit of sargassum. Actually, when you calculate the potential or like the coverage of the sargassum at the surface versus in the deep sea, it's more in the deep sea than at the surface, because of course the deep sea is like the ultimate sediment trap, and it accumulates what has been falling in the last years. And so, yeah, you find it there.
Yeah, I'm still very impressed by finding the algae in the Arctic still alive on the bottom of the seafloor. So
I was very impressed by that as well. We measured primary productivity in them just because I couldn't believe that they looked so healthy.
Yeah, I can totally understand that was a surprise. Yeah, wow. And so there's more questions coming up about how to use the sargassum already now. And WOW 83 has at least its fingers crossed that it will all work out, and to have pilot scale research projects around it. And about the concrete, is that already produced, or is it still in research scale?
No, there is a company already in Mexico and one that is French, but I don't know where they're based. But there's definitely a company in Mexico that have created a product that they call Sargacreto. So it's like the concrete made of sargassum. So this is already happening. Yeah.
Wow, super. That's cool. Yeah, and I mean, I just some weeks ago heard also that there's the promotion of buildings and stuff with wood. So then combining it with concrete made of algae, I think that would be perfect combination.
Yeah, because actually producing concrete produces a lot of CO2, the process.
Yeah, it's really fascinating. But I mean, of course, if you think about like doing that large scale, so I'm wondering, like, could it really be a game changer? I mean, how much would we have to bring down? How expensive would that be? I mean, there was also another comment by WOW in the chat. Of course, the good potential for a pilot study, and it's all very exciting, and I agree. And I mean, we talked about that before. But I mean, I could also imagine it's kind of so hugely expensive to get that done, and the reward is kind of so small in terms of CO2. Do you have any numbers there and can comment on that?
So I would say, first of all, yes, we're in the verge of a revolution, like the same type of revolution we had back then with agriculture on land. We basically have to irrigate the oceans and start doing that in the ocean. So it's a completely new economy that needs to be built around it. And so it is true that as it currently is, you don't get enough money from CO2 carbon credits to actually make that work, because the carbon credits are still too cheap, or let's say the ton of CO2 is still too cheap. But that's going to change. That's the first thing. But what companies that try to make a business assessment about this and an economical plan on how to make this viable, what they say is, okay, let me first look at which type of products can I sell at which price. And from sargassum, for example, you can extract alginates and fucoidan, and those things you can sell for like $5,000 the kilo. And so if you start with those things that are irrelevant for the CO2 climate crisis, right? But they give you the revenue and the money to start things going. Then when the carbon credit price goes up, then you can move on to start sinking the CO2. And of course, I think the bottleneck here is not actually the money itself, but rather the infrastructure. I think the bottleneck is the engineering that we need to make this happen in a safe way, the monitoring that needs to be associated to it. And if we want to do this offshore, which is where we have space, because the coasts are basically already so full with other stuff that in the coast we don't have the space to fix the amounts of carbon that we need to fix. So if we go offshore, which is what we need to do to upscale this in a feasible manner, we need infrastructure, we need offshore aqua farming structures that can withstand this. Now, you might think this is something that belongs to the future, but actually there are companies, for example, Norwegian companies that are already taking their salmon farms offshore. And so they are developing the structures and everything to make this feasible. And you must think about this. The oil companies, they've managed to drill for oil in the Arctic, with all the ice moving around and whatever. So it's just a matter of putting the best brilliant minds in terms of engineering and whatever to the topic and say, okay, this is what we need to do. make it possible and feasible economically speaking. And I think it will happen. I hope.
Wow, I really like that hope there, and then how easily you tell us that, or how feasible actually you express it. So it's really get actions on it. And regarding some kind of other products for producing, here Hans-Fritz Peter was saying, you mentioned how many shoes would be produced per amount of sargassum. Are there actually shoes produced by that?
Yeah, you can.
If you know another company in it.
Yeah, you can buy them in Mexico. I mean, I think you just need to Google sargassum shoes and then you'll find it. There's also soap made of sargassum. There's paper made of sargassum, ink made of sargassum, fertilizer made of sargassum. So you can buy already a lot of products made out of sargassum. Yeah.
And in this sense, or in this direction, do you have also some numbers of how much that means in reducing the carbon from atmosphere? So, for example, how much kilograms of macroalgae from Sargassum or from the Melosida that you also mentioned means of reducing carbon?
So you mean for the global carbon budget? Okay. So from the uses, like from building bioplastic or whatever, I don't think there's any estimate at the moment because it's mostly small companies doing small things, and so no one has really added them together. But the potential for carbon sequestration of this algae, it basically depends how much you grow of them. So, I mean, at the moment, I think the latest papers published said that in terms of carbon is like 0.8 pentagrams of carbon in the sargassum right now. But again, the literature ranges from that to 13 pentagrams of carbon that could be in the potential area where sargassum could grow. So I think the literature is not yet like, okay, we know this for sure. We're still learning about it because it's also a relatively new process, like it started in 2011. And so I don't think we have numbers, and I don't think the modelers have actually done any proper modeling yet as of the potential, but basically because they're lacking the numbers. They don't know the remineralization rates of sargassum. They don't know the primary productivity rates of sargassum in the middle of the Atlantic. And so all these things still need to be measured. Like scientists still have a lot to do.
Yeah, that's a really good conclusion of there's still some work to do, but also as you mentioned before, if we can also not do nothing. So I think even if we stop emitting CO2 at this very moment, we still will need to get rid of all the stuff that is there too much already. But then going more in towards what needs to be done to get this sargassum at the bottom of the seafloor was the question by Ole Müller again. What does it take to artificially sink the sargassum? So in a technological way.
You just need a press. So there are several ways. There's a company called SOS Carbon that is basically absorbing the sargassum, putting it into a funnel and sinking it down to 200 meters where the bladders explode and then it sinks automatically. The problem of that is that it's difficult to track once it's sunk down. That would be one way, and you don't need to do much. Another way would be to compress it into bales and then basically drop it. I mean, naturally it sinks like 40 meters per second or something. So if you bale it, it will go even faster. So it will really reach the deep sea really fast. I mean, it depends on the depth, but yeah, that is not, I think that's not the complicated side of things.
So Shishong, or whatever, however that is pronounced, asked another question more into the technical direction. If something similar to these bricks, hemp limestone bricks, would also work with sargassum and limestone, and if something like this would further increase the amount of CO2 that's trapped as none of is released anymore from these kind of bricks. I mean, it's something that you mentioned already.
So mixing ocean alkalinity enhancement with macroalgae sinking, I hadn't thought about that, but why not actually? I mean, the thing with limestone and all these things is that you get a little bit into trouble with the London Protocol. So we're actually not allowed to dump anything into the ocean. Like that's why iron fertilization is not allowed anymore. So also putting limestone in to enhance alkalinity would be an issue according to the current regulations, which hopefully will change. And so if you add then limestone to your bales, you're adding something and dumping something extra. Because one thing that I thought about, for example, is that if you would wrap those bales in, let's say, for example, in salt, Victor mentioned that, Victor's method check, putting them in salt or even in plastic, like wrapping them in something that makes them inaccessible for any form or organism to decompose them, that would be even more efficient, the sinking and the carbon sequestration. But then you get into, you're dumping other things into the ocean and you don't really want to go there. So I don't know, one could think about it to put together ocean alkalinity enhancement with macroalgae. Yeah. I'm open for ideas. Sure.
That's great. We also have another fun, actually, Inavi from algae farming. And here, Hannah, it's mentioning if you have discussing your ideas with Victor Schmettak. Sorry, I'm having problems to pronounce his surname because he's really one stronger algae farming. And we also have a comment, or a question actually, sorry, from Oahu, who says, do you have any Sargassum product at home?
Me? Unfortunately not, but as soon as I go to the Caribbean, when I'm allowed to travel again to do research, then I will buy all the soaps and to have examples at home. Yeah, no, but not right now, unfortunately. But my work colleague, Francisca Elmer, the co-host, the owner of the Sargassum Podcast, she has a lot at her place. And when we do interviews, they all show us like, look, I did this with Sargassum. So we've seen paper, ink, a lot of really cool things, fertilizer.
Wow, that's cool. Yeah, I think that was a good advertisement for watching the podcast or listening to it. And I can also highly recommend it. And the question of if you have discussed it with Victor's method check, he was also on that podcast already. So I think that's...
Exactly. So he's the one with the big vision, actually.
Cool. Yeah, thanks a lot. And I think there's at the moment no further question in the chat, but with all these questions that we had already, I think that shows the interest and the excitement that also jumped from you to the people, to the watching the video. I think that's, was not climate optimist is definitely a good name for having a vision and bringing good ideas how we can control or at least do something in the future about our CO2 problem. And with that, if you have any further question thinking about it or dreaming about the talk tonight, then just write them below the video tomorrow or any other day, and we will forward the questions to Mar and try to give you information. And I just say thanks again. Thanks for also joining Matthias and Cami, and then have a nice evening.
Thank you.
Bye.
See you next time.
Wissenschaft fürs